Yeah, so I'm going to talk about general relativity, and in particular, a part of the theory that fascinates me the most, sort of what I call the strong field regime of general relativity, or the extreme side of gravity. So what lives in the strong field regime in this extreme side are black holes. And in particular, one of the more interesting aspects of this is the dynamical strong field, and that's where black hole collisions reside. So here's an outline of my talk. So to introduce the strong field, I'm going to talk about the contrast gravity between Newton's theory and Einstein's theory of general relativity. And then I want to describe this extreme side of space-time, and that's when gravitational collapse happens and black holes form. Now, I could probably spend a whole lecture just talking about black holes. There's so many interesting things about gravity, or black holes as described by Einstein's theory. But I'll just describe one particular part of black holes and extreme gravity that I think is particularly fascinating, and also hopefully just to sort of inspire you to think, well, these objects are crazy. And so, like, do they really exist? Is this just a theorist's fantasy, or do black holes actually exist? And well, sort of the answer, science can't prove things like that definitively, so especially with astronomical objects. But over the last few decades, the evidence has been growing and growing, and I'd say it's almost incontrovertible now that black holes really do exist. And what's particularly exciting in the last few years, as Andy mentioned, is, well, in particular 4 years ago, LIGO started observing gravitational waves from black hole collisions. And this is now a whole new level of direct evidence that tells us black holes exist. So I'll explain a little bit about gravitational waves, and then I'll sort of show you like what aspects of the signals, or why do we say that the signals that LIGO has shown us actually is coming from the collisions of black holes? What is this evidence that these very strange and fascinating objects actually exist, as described by Einstein's theory of general relativity? Okay, so let's sort of begin with Newton's theory of gravity, which is now well over 300 years old. And so in 1687, Newton came up with his universal law of gravitation, sort of consistent with his Newtonian mechanics framework, where gravity was one of the forces that could exist in nature. And it's a very particular force, and he came up with a very elegant description for this, the so-called universal law of gravitation. And essentially it says that any two objects in the universe feel an instantaneous force of attraction between them, and the strength of the force is proportional to the masses of the objects, and it diminishes with the inverse square of the distance between the objects. So mathematically, quite a simple description, but very successful. So prior to Newton, for example, there were theories that described how the planets evolved, the moon around the earth around the sun, but it was quite complicated and convoluted. This theory came up with a very simple sort of mathematical framework that explained the planetary behavior very successfully. And incidentally, it also explains perhaps a rather unintuitive thing about gravity, the Galileo experiment, when Galileo sort of apocryphally stood on top of the Leaning Tower of Pisa and dropped two items, one, say, a feather and a heavy ball. And if you ignore the friction of the Earth's atmosphere and other forces, they fall at the same rate, which sounds quite bizarre. How is it possible that one thing which is so light and one thing which is so heavy falls at exactly the same rate? And it's not that Newton's gravity perhaps explains it, but it comes up with a mathematical device that predicts that, in the sense that the force is proportional to the masses of the object. So it's kind of strange that this force can somehow adjust itself instantaneously to the masses of the two objects that are experiencing this gravitational force. But that's what nature seems to suggest, and it was successful in describing that. Okay, so fast forward to the early 1900s, and Einstein came up with his theories of general relativity. And I'm putting this in gravity here in quotes, because Einstein's theories really aren't theories about gravity. They're actually theories about the structure and the nature of space and time. We call them space-time. So it sort of says that space and time aren't necessarily independent concepts. They're aspects of the same sort of reality. And the way in which Einstein describes space-time, he said that we can describe it as a geometric structure. So both special relativity and general relativity are theories about space-time. In a sense, the difference is in special relativity, this geometric description of space and time is given by fiat. It's just said, well, this is what space-time's like. It's a completely flat four-dimensional geometry, and it's unchanging. And the theory of special relativity essentially tells us, well, how do we understand that? How do we experience it? How do we move through this unchanging geometry? In general relativity, the difference, at least the colloquial difference is now geometry can actually be curved, and it can be dynamical. It can change. So they're both theories about space-time. General relativity says geometry is curved and dynamical. Special relativity, in some sense, then is a special case of general relativity, where space-time is just given by this flat geometry called the Minkowski space-time. Okay, so where do we get gravity from curvature? And so, this is a kind of a very schematic description of general relativity. And general relativity is actually quite a complicated theory because it's not just saying space-time is geometry. It's also telling you exactly how the geometry can arise, how it can become curved. And through the Einstein field equations, it sort of gives it in mathematical detail, but essentially what it says is that all forms of matter and energy in the universe cause space-time to become curved, or they bend space-time. And that's sort of what this this graphic is sort of representing. So the Earth has a lot of matter energy, and it's bending space-time around it. And the Einstein field equations say exactly how a particular amount of matter and energy bends space-time. Now, the other thing that the theory has to then tell us, it's not just how space-time is bent, and this is also true with special relativity, even with a flat space-time, is how we, or observers, experience a curved space-time. What does it mean for us to live in a curved space-time? And so essentially, what it says is that observers, that you're an observer, so we also have matter energy, so in some sense we are also bending space-time, but an observer in this language is an object which has so little energy compared to something else that the amount of bending that it does is insignificant. So an observer responds to the curvature of something that really bends space-time in a lot, say the Earth, for example, by following what's called the geodesic of that geometry. So it's in some sense the optimal path through that space-time. So for example, on a flat surface, or in special relativity, the geodesics are just straight lines between 2 points, so the shortest distance between 2 points. If you look at an example of a curved geometry, say the surface of the Earth, and you say if you just restrict your motion to the surface of the Earth, what is the quickest way to go from one point to the other? You follow one of the great circles. And that's a geodesic on the surface of the Earth. So Einstein's theory says, well, matter and energy curve space-time, and then the way that we experience a curved space-time is if there are no other forces acting on us, we follow these optimal geodesics through space-time. Okay, so where does gravity come from? And this is perhaps the fascinating thing is that gravity, this notion that space-time is curved and that matter curves in a particular way actually completely does away with gravity as a force. So for example, let's think about again the Earth. So the Earth is a very heavy, massive object compared to us. So the Earth curves space-time in a way which is quite strong. We curve space-time so insignificantly compared to the Earth that we can be considered observers or test bodies that want to follow the geodesics of Earth. So Newton's theory would say, well, no, there's a force between each one of us and the Earth, the GMM over r squared force, and that's the force of attraction. So the Earth is pulling us towards it and vice versa. Einstein says, no, that's not the case. Instead, the Earth is curving space-time in a particular way. And then the question is, well, how do we want to follow that curvature through geodesics? And the geodesics of the space-time around the Earth are those where we'd want to fall towards the center of the Earth. So what you sort of intuitively think of the force of gravity in Einstein's picture is actually not gravity at all. It's all the other forces that are keeping you, that are pressing against you on your chair, that are pressing up against my shoes here, and they're mostly electromagnetic forces that are preventing you from following geodesics. That's sort of how you should think about what you feel is a force of gravity. It's actually other forces that are stopping you from following geodesics. Now, so that's, I think, it's from the philosophical perspective, it's fascinating that the same physical phenomena, it's still, let's call it gravity, whether it's Newton or Einstein, can be described by such completely different frameworks. One is a force, the other is a curved space-time geometry. And of course, if that's all that general relativity was, I think we said, yeah, it's cute, but the field equations are actually very, very complicated. Newton's laws are quite simple, so why do we bother with relativity? Well, the first reason is that when Einstein first came up with it, there were several anomalies that Newton's theory didn't quite explain. Well, the main one was the perihelion precession of Mercury, the fact that Mercury's orbit doesn't close, and Einstein theory explained it. And then very soon afterwards, with the Eddington's expedition that measured the deflection of light from starlight passing the sun, that was also consistent with Einstein's theory. And even today, GPS, if you use GPS to locate yourself, the fact that we could do it as accurately as we can, we need general relativistic corrections. So nature is telling us that even if those changes are small, general relativity is the correct description, in that sense, whereas Newton's is not. So the space-time description seems to be correct. Now you can say, okay, right, so that now from a physics perspective, we have a slightly more accurate theory, we've got a better description of nature, but is it just little corrections to Newtonian gravity, like tiny little precessions of planets, a little bit of deflection of light, or a bit more accurate GPS localization? And the answer is that no, that there are certain regimes where things are not just corrections, they're significantly different. And that's when we get to the extreme side of gravity, or the strong field regime. So to motivate or to describe what I mean by strong field, let's ask about strong gravity, and let's first do it in the Newtonian way of thinking about it. So let's ask this question: so how strong can the gravitational force be, and what happens when it becomes, quotes, very strong? Well, in Newton's theory, you can sort of anticipate this from the form of the expression. Perhaps another way of thinking about it is that Newton's theory is a linear theory. So the answer is it can become arbitrarily strong. You can make the mass as large as you want. You can put the mass in a small enough thing. You can go as close to the center of the mass as you want. So it can become arbitrarily strong, but nothing qualitatively changed. The force is just that much stronger. So now let's ask the same question in Einstein's theory. But now let's flip to the correct way of thinking about gravity in Einstein's theory, that it's not a force, it's curved space-time. So the corresponding question would be, how curved can space-time become? And what happens when it becomes, quote, very curved? And here I think it will be useful to introduce another aspect of curved space-time to describe this, and this is what's called gravitational time dilation. So another thing, so not only does the Earth sort of curve space-time in a way that affects our natural path through space-time, but there are other consequences of curvature. One is this gravitational time dilation. And here's sort of an example of a little experiment a thought experiment to demonstrate what it is. So the Earth is curving space-time, and similar to Newtonian physics, well, it has to be similar because it explains things quite well, that the further from the Earth you are, the less the curvature is in space-time. So close to the Earth, there's a lot of curvature because of the Earth. Far from the space-time, there's less curvature. And so what gravitational time dilation is that the way in which a clock runs when you're in a high curvature regime relative to some distant curvature, clocks slow down when you're closer to strong curvature. So here's sort of the thought experiment. So take two clocks, identical, synchronize them very far from the region of curvature. Now take one clock, move it down, say, to the surface of the Earth, and let them run for a while, and then take this clock and move it back up to the other one, and you'll notice that the one that spent a lot more time in the strong curvature, less time has elapsed. And that's this gravitational time dilation effect. And incidentally, it's a purely relative effect, so perhaps that's one reason why Einstein's theory was a theory of relativity. In special relativity, there's length contraction, there's time dilation that is associated with relative velocities. The same is true with relativity, but now there are additional ways in which you can get these strange relative effects, but it's all relative. So, you never experience your local clock going slower, or this one going faster. It's always a relative comparison between things. And here, this aspect of general relativity is that curvature changes the rate at which the clocks flow relative to one another. But it's not really something that you would notice locally. Okay, so this is another aspect about what curvature does to space-time and how we experience that. And so now you can say, well, okay, so now how do we get, what does that mean in terms of like strong gravity? So how much time dilation we can get? And here also the Newtonian notions are useful in the sense that you can imagine if there's more mass, there's going to be more time dilation. If you make things smaller, the same amount of mass in a smaller region, and you get closer to that center, there's also going to be more time dilation. So for example, here are 3 examples of massive objects not drawn to relative scale. Here's the Earth, 12,000 kilometers in diameter, this amount of mass. And for the Earth, roughly the time dilation of a clock on the surface of the Earth relative to one very, very far away is 0.7 nanoseconds per second. So that's the rate at which clocks, relatively speaking, will be running slower on the Earth. And so of course, that's a very small amount. But interestingly, it's large enough that it's with GPS satellites, that's sort of an example of where relativity is used today on Earth, is they're a few hundred kilometers up orbiting the Earth. And it's through precise timing and triangulation that we can sort of localize ourselves. But this difference is enough that it has to be taken into account to get accurate localization. Now let's go to another massive object, the Sun. And here we have sort of 2 competing effects that will affect the time dilation. So the one is the Sun is much larger in diameter than the Earth. So if some object is larger, the time dilation is going to be less. But the Sun is also much, much more massive than the Earth, so that's going to increase it. And so if you work out, it turns out that the extra mass of the Sun wins, and so on the surface of the Sun, this time dilation is about 2 microseconds per second. Now let's go to one of the most sort of massive, compact material objects that we know of in the universe, neutron stars. So neutron stars are the remnants of old massive stars that they've burnt up all the nuclear fuel, they've undergone partial gravitational collapse, and they've ended up in this very, very dense state. So a typical neutron star is about 25 kilometers across, so basically the size of Manhattan. But there's usually like about 1.5 times the mass of the Sun that's packed into that small region. So incredibly dense objects, almost unimaginably dense. And if you could sort of sit there on the surface of a neutron star, you'd notice that the time dilation was 0.3 seconds per second. So that's quite significant. You wouldn't need fancy GPS satellites to tell you that there's significant time dilation. Okay, so now let's go back to our question in Einstein's theory of gravity. So thinking about curvature as a measure of strong gravity. So we want to say, how curved can space-time become when it becomes very curved? And now we can say, well, Newton's gravity and Einstein's gravity was the same description effectively for forces. So let's use that intuition to answer this question. So if Newton and Einstein are pretty much the same kind of phenomenon, then don't we already know the answer? It says, so remember with Newton's gravity, it was forces can become arbitrarily large, but nothing qualitatively changes. So if that were the answer, it would be gravitational time dilation can become arbitrarily large, but nothing qualitatively changes. The clocks just seem to run that much slower. And part of this answer is correct. Yes, the time dilation can become arbitrarily large, but something does qualitatively change, and that's this gravitational collapse to a black hole. So let me sort of, right, so this is, so that's what I said. So the answer is, again, time dilation becomes arbitrarily large, but the interesting thing is that it actually doesn't happen at arbitrarily large curvatures. At finite curvatures, you can get infinite time dilation, and when that happens, then the nature of space-time qualitatively changes, and a part of the space-time undergoes what's called gravitational collapse, and it forms a black hole. So to illustrate, let's imagine sort of going along a sequence of ever sort of more compact objects, and then eventually collapse happens. So again, using this sort of cartoonish picture of the star producing curvature. So here's a star, say the mass of the sun, it produces a bit of curvature, there's a little bit of time dilation. Now we go a little bit denser, something called a white dwarf. So for example, if this, as neutron stars were so the remnants of old stars that had lost all their nuclear fuel, but those are stars that are a few times more massive than the sun. Once the sun expends all of its nuclear fuel in 4 billion years or so, it will undergo a supernova, and the remnant will collapse down to something called a white dwarf. So it'll be a little less massive than the sun, but almost as massive than the sun, and about the size of the Earth. So a very dense object. The curvature is going to be a lot stronger. We continue going, so now to neutron stars again. Here the curvature is quite strong. We get that 0.3 seconds per second. But now if you take the amount of mass of a neutron star in that radius, 25 kilometers, and you somehow compressed it by a factor of around 2 or 3, so around down to, say, 10 kilometers, then this gravitational collapse would start happening. So you'll notice what will happen is there'll be a surface where the time dilation will actually go to infinity. That's what we call the event horizon of the black hole. And inside the event horizon, the nature of space-time qualitatively changes. So if you did this little experiment of measuring time dilation, if you could hover right at this event horizon, clocks would essentially freeze compared to exterior clocks. So the time dilation has actually gone to infinity at that point. And so now you've mentioned, well, let's continue. Let's hover just inside the event horizon. Is it going beyond infinity? Well, no. And the reason is that it's impossible to hover inside the event horizon. And the reason is space-time has changed its character. Whereas outside, you'd notice that there's large curvature, there's large time dilation. But for a non-rotating black hole, that's called a Schwarzschild black hole, you'd say the space-time is static. It's not changing. The curvature is large, but it's not changing. Once you cross the horizon, space-time becomes dynamical. And all of space-time flows down to an actual singularity in the curvature somewhere inside the black hole. So perhaps another way to sort of illustrate like how what this qualitative change in the character is from being static to dynamic is if you're outside the black hole and it's a static black hole, so we have our coordinate, say the radius, which is our distance from the black hole, and we're sitting some distance from it, and we can say, well, where's the event horizon? It's over there. I'm, say, at a radius of 10, say it's at 1. And there inside the black hole, theory tells me there's a bad singularity, so I should avoid going there. And I'm looking and my clock's running, and my clock is going at something, let's call it the time coordinate t. But inside the black hole, it turns out that space-time becomes so curved, so twisted, that time and radius flip character. Time, what used to be your time coordinate becomes a distance, and what was radius becomes a time. And going forwards in time means you go to smaller radius. And so all of time is flowing down to the central singularity. So what that means is, okay, so outside, radius is distance. I say, where's the singularity? It's over there. I've listened to this lecture that said, don't cross the horizon of the black hole, but then you go browsing your phone, you kind of lose track of things, and instead of walking into a tree like I sometimes do, you at some point say, oh crap, I've crossed the horizon. And now you start panicking because there's a singularity and say, where's the singularity? Where's the singularity? And that's the wrong question. Outside, you can ask where the singularity. Inside, it's when is the singularity? And the answer, it's in your future. So once you've crossed the horizon, you can accelerate in any direction you want, go as fast as you want. But since you're always going forwards in time, you'll always run into the singularity. And incidentally, a tip is if you do cross an event horizon like that, and for very massive black holes, it could be a while before you die. But to extend your life by the longest amount of time, don't do anything, just relax. Go into free fall. Any acceleration that you do will get you there faster. So turn off your rocket engine and just enjoy the last few seconds of your life. Okay, so I think that's a pretty fantastical prediction of what happens to space-time. And it sounds almost crazy and ridiculous. So the question is that just a fanciful aspect of the theory, or do black holes actually exist in nature? Is this actually happening? Are there regions of space-time where event horizons are forming, space-time's changing character, and all of this crazy stuff is happening? And at least so far, the answer seems to be yes. And the evidence has been gathering for the last few decades. And so the examples of the evidence that I'm showing here are what I'm calling circumstantial evidence. It's been getting very, very strong, but it's circumstantial in the sense we're actually not seeing aspects that are coming from curvature itself. We're seeing other matter. So we're seeing matter that are trying to follow these geodesics. They're following the geodesic hypothesis. But it's not showing us something directly about curvature itself. So for example, perhaps one of the first candidate black holes that was discovered was Cygnus X1 in the 70s. And what is seen is a star with a very peculiar X-ray feature coming from it. So we don't see a black hole, but what the interpretation of that is that there's a star in orbit about a black hole. The black hole is consuming matter from the star. That matter heats up, and as it gets very close to the black hole, it starts emitting in X-rays. So we see X-rays coming from a star. It's very puzzling to explain if we didn't have this black hole hypothesis. With a black hole, that X-ray emission is sensible. Another great example are stars orbiting the center of our galaxy, so-called Sag A star. And astronomers have sort of tracked the orbits of stars for a couple of decades now. And so these are, you can see the orbits around the center. And if you just apply Kepler's laws and say, well, how much mass has to be there to explain these orbits? It's something like 4 million times the mass of the sun. But look, there's nothing there. How can things orbit? How can something that's 4 million times the mass of the sun be invisible in optical? And it's actually visible in radio, but say in optical you don't see anything. Well, a black hole is a consistent explanation. But again, this evidence then for the black hole is not the black hole itself, it's the stars going around it. And perhaps one of the most recent sort of spectacular pieces of evidence comes from the Event Horizon Telescope, that you've probably all seen. And this is the so-called shadow of M87. It's a monster black hole. So this is like 4 million times the mass of the sun. This is about 1,000 times more massive. So it's over 1 billion times the mass of the sun in M87. But again, what you're seeing here is it's not the black hole. The emission here is, again, presumably matter that's in an accretion disk around the black hole. And the way in which the accretion disk is evolving around the black hole and the light is traveling around creates this sort of characteristic shape with a shadow. Again, completely consistent with black holes, but I would say it's circumstantial, it's indirect evidence. It's very strong. And when people have over the decades tried to explain all of these phenomena, well, this is not that recent, this is not that old, using other ideas other than black holes, and there really are no convincing ones. So that's perhaps a decent argument for it being black holes, but in some sense, they're such extraordinary objects. Sort of paraphrasing Carl Sagan, we need extraordinary evidence to say that we're really getting black holes as predicted by relativity. And I think, in addition to all of this evidence, now a completely new way of looking at space-time has been given to us by LIGO, and that's by looking not at the way in which matter behaves around black holes, but in the gravitational waves that are emitted when black holes collide. So, incidentally, these black holes, they're all, again, very massive compared to the matter that's going around them. So all of the matter is like observers. It doesn't change the space-time. And in that sense, these black holes are all static. They're just sitting there. They're actually not emitting gravitational waves. If you want to probe black holes using sort of the fabric of space-time itself, gravitational waves, it turns out that you need black holes to collide. A single black hole doesn't emit anything, and so that's why we want to look at black hole collisions to try to get direct evidence for the existence of black holes. So in general relativity, right, so that's what I said. So in Einstein's theory, well, what produces gravitational waves? So I said matter and energy produces curvature. So if matter and energy is changing, the curvature is changing, and that the changing curvature then causes gravitational waves to be emitted. And so gravitational waves are these ripples in the geometry of space-time that propagate outward at the speed of light. Okay, so if you want to sort of think of an analogous process, it's very much analogous to electromagnetism. So in electromagnetism, if you have electrons or protons, charged particles, you accelerate them, they emit photons. They emit or in the classical description, they're going to emit electromagnetic radiation. And so, of course, with photons, with electromagnetism, we can set up transmitters and receivers, and we can build radios and televisions and all of these stuff. And so in theory, you could do the same thing with gravitational waves. We can have matter that's accelerating. I'm waving my arms around. I'm producing gravitational waves. And we can build up a receiver that measures it. The problem is that space-time is, in some sense, very stiff. And the kinds of gravitational waves that we could, in principle, produce on Earth are so weak, there's really no hope that we'll be able to measure them in, well, I don't know, I don't want to make predictions how many lifetimes it might take, but it's really basically impractical. And so to see gravitation, or to actually find gravitational waves, we have to look to extreme events in the universe, which could produce very large distortions in space-time that we might be able to measure. And the best possible candidate is taking the most dense objects, the most dense concentrations of energy, and smashing them together about as fast as you can. And in nature, the one phenomena that captures that is the collision of black holes. Now, incidentally, the nice thing about this, so I mean, I'm sure like all you've heard about LIGO, and as Andy had mentioned, mentioned that as well, and I'll explain a little bit more about that. And so the way that I'm describing, at least that I've sort of described it here, is you think, well, we have to build these detectors so we can look at gravitational waves, and that's really not, that's not, the reason is not to sort of set up a receiver detector or one side of the thing. The thing is actually to really observe the universe. It's not just to show that gravitational waves exist. It's a new way of actually looking at the universe, observing them. So we've seen, LIGO has seen black holes collide, they've seen neutron stars collide, but they made the other things that we hope to see through gravitational waves. So it's really a new way of looking at the universe. Okay, so let me give you, to briefly describe what gravitational waves are, sort of slightly more quantitatively. So what we're going to eventually look at is two black holes. They're going to be whirling around each other. They're going to smash together. They're going to produce gravitational waves. So this collision is in the strong field extreme part of a relativity. But then the waves are produced and they propagate away from the strong field into what's called a weak field. And eventually they cross us here at Earth. And then that's sort of that's a weak field description. And that's what we measure. So the weak field nature of gravitational waves is sort of as depicted here. So it turns out that there are two so-called polarizations of gravitational waves. One is the plus polarization is just a rotated version of the cross. So qualitatively they're the same, but they're two polarizations. And so what this graphic is supposed to depict is, again, it's ripples in geometry, space-time. Perhaps the best way to think about it is, well, how does it affect geodesics? How does it affect this optimal path through space-time? And so imagine sort of a ring of geodesics, so there's no other forces acting on them. It turns out that gravitational waves only affect distances transverse to the direction of propagation. So here imagine a gravitational wave that's going straight into the screen. It's not going to produce any motion in the direction of the screen. But as a cycle of the wave passes, so imagine sort of a sinusoidal cycle, at one instant it's going to stretch one direction, say the vertical direction, while simultaneously squeezing the horizontal, and vice versa. So as the cycle of the gravitational wave passes, it's this oscillatory stretching and squeezing sort of in the plane that's transverse to the direction of propagation. So to detect a gravitational wave, you have to come up with an instrument that can measure the change in distances between test particles. So it's basically you need a very accurate ruler. And that's what the LIGO instrument is. But I mentioned space-time is very, very stiff. So even a cataclysmic event like a binary black hole collision, by the time the wave gets to Earth, it's very, very weak. So you need an incredibly accurate instrument. And in some sense, you want to take advantage of this nature of the gravitational wave, that at one instant it stretches in one direction, but in the orthogonal direction it squeezes. And so that's what that's why the LIGO detectors have these sort of L-shaped configurations. So they essentially these so-called Michelson interferometers. So a laser goes to a beam splitter, it runs down these two arms, and then when the laser light comes back to the original source, there's interference if they travel along different distances along the arms. So in this case, the gravitational, say in this example, it's most sensitive to gravitational waves that are coming directly down into the detector from above or from below. So gravitational waves can pass through the Earth unabsorbed or undeflected. But essentially, this is really just to take advantage of the stretching and squeezing. So a perfectly oriented gravitational wave, at one instant it will squeeze one direction while stretching the other one, and so you'll get this interference pattern at the source. Now, if you haven't had a lecture on LIGO, I'd very recommend you do on just the experiment. It's an astonishingly accurate machine, almost mind-boggling that they were able to pull off such accurate measurements, but they have, and it's very worthwhile to look a little bit about the experiment. But I'm not going to talk anything more about LIGO because I want to talk about black holes. So it's been a decade's effort to get LIGO sensitive enough to start seeing these ripples in the geometry, and the first event happened about 4 years ago. This is the amplitude of this fractional stretching and squeezing here by the two LIGO detectors, and since then many other black hole mergers have been detected, and one binary neutron star merger has been detected. So now I want to explain in the last few minutes of my talk why these little wiggles, so why we can interpret them as coming from the collisions of black holes, and then you can sort of judge for yourself how good this evidence is for black holes. And incidentally, I should mention, I think it was on a slide, but I forgot to say. So perhaps, at least perhaps to me, like one of the most remarkable pictures about gravitational collapse is that time changes. Time and distance switch characters. So space-time is static outside, it's dynamical inside. But what that does is it also creates this event horizon. So it seals off the interior completely from the exterior. And unfortunately, gravitational waves, they also experience space-time. If they're inside the black hole, they're also going to get swept to the singularity. They can't escape. And so if the general relativity picture of black hole is correct, we'll never be able to see the inside. So the best we can do with saying, like, do black holes exist, is probe the exterior and sort of see that things are approaching this infinite time dilation, but we can never go inside the horizon. So gravitational waves are not going to answer perhaps that part of the question, but we can get as much information about the space-time around black holes with these kinds of events. So again, so this was the first one observed. A gravitational wave came past the Earth. You can see it's kind of a slightly ratty signal. Well, that's noise. It's a real instrument. It's noisy. But this is perhaps a slightly clean version of it, and this is what we interpret as a gravitational wave. So I want to explain exactly what's going into that signal, at least as we understand it from a theory perspective. So what we think these things are is that two black holes were in orbit and they collided. Well, why would they collide? I mean, it's not that people say black holes suck in everything. That's not true. And the thing in general relativity, the interesting thing is any two objects in orbit, so they're the two-body problem, say the Earth going around the sun, the moon going around the Earth, in general relativity, that's an unstable system. And the reason it's unstable is because of gravitational waves. And here you can also use your Newtonian intuition about energies and binding energies. So in a bound system, so two objects are orbiting each other, there's a certain amount of energy in that system. And now if that system loses energy, it becomes more tightly bound. And what happens with two objects in orbit, being more tightly bound means they get closer to each other. So there's energy in the curvature of space-time. Gravitational waves are a manifestation of curvature. So if two objects are orbiting each other, so the space-time structure is changing because you've got these two concentrations of mass that are moving around each other. So that produces gravitational waves of energy. So the system is losing energy. And so because it's losing energy, it becomes more tightly bound, and so then they start orbiting more closely. So any object in orbit will do that. The rate is very, very slow for common stuff. So don't worry about the Earth spiraling into the sun because of gravitational wave emission. That's not going to happen in gazillion years. But if you have a very massive, dense object like black holes, that could actually lose quite a lot of energy to gravitational waves, and it's a runaway process. So they spiral around each other, they lose energy, they become more tightly bound, but now they're closer to each other, so they're going faster, so they emit more energy, they spiral even faster, and eventually they meet up. And so what happens with black holes, at least from solving the Einstein equations, what we know what happens when two horizons, so these two regions of space-time inside which are undergoing gravitational collapse of these horizons, is that these two regions of space-time, when they meet, they glom together and form a larger horizon. And then very, very quickly, it's initially very distorted and dynamical, but it also emits radiation, and it settles down to a quiescent black hole. And that's the so-called quasi-normal ring-down phase of a black hole. So that's why two black holes find themselves in orbit. And for example, how that might happen even before that is you have two stars, very massive stars, they run out of nuclear fuel, they start to collapse, but they're so heavy that even the neutron star phase is not strong enough to support them against collapse. Then they'll collapse to form black holes. Now you have two black holes in orbit, and then this gravitational wave emission will eventually drive them to merge. And what LIGO sees is the very, very last stage of that merger process. So here's an animation by the Caltech, Cornell, CEDA, now a Max Planck group, sort of illustrating this for parameters set up that mimics that first event that LIGO saw. So there you can see the two little black holes. And so actually those black holes that LIGO saw, yeah, they're small, but they're actually quite large, relatively, well, they're quite massive, relatively speaking, but they're on the order of a few hundred kilometers in size. And so here's, if you will, if you were to convert this to a real-time scale, this would be the scale. So that's about 1,000 kilometers or 600 miles. And as you'll see, you know, they're spiraling around each other, but actually, so as I'll show you with the LIGO plot, this event happened very, very fast. So this animation is actually slowed down by a lot, by about a factor of 100. So this whole thing happened this whole animation in that event took place in a few milliseconds. And the reason is these black holes are, at this last stage, they're orbiting very close to the speed of light, perhaps 20-30% the speed of light. So it's an incredibly rapid motion and sort of a violent collision in that respect. And so now you can see they're going around each other. So that the ghostly green light, that's the depiction of the gravitational waves. So you can see that the color, the intensity is getting larger. That's because the emission's getting stronger because it's this runaway process. And eventually, you know, you'll see that they'll merge together. And then very rapidly after they merge, you can almost not see it there. So there was this ring down. So it was a distorted thing, but it happens incredibly rapidly. It settles down to this quiescent object, and then the waves just stream away. And with this event, you know, this happened about 1 billion light years ago. It started streaming away, and 1 billion years later, it washed across Earth, and that's what LIGO saw. So this is that very last stage, is the last few orbits that you saw, and that merger and ring down. And so now I can perhaps explain a little, like why then do we think that this is coming from that system? Like what features of this wave are telling us it's a black hole, some properties about it, and that it merged into a black hole? Well, the first thing that you can almost immediately see from this is this runaway in spiral. So if two black holes are in orbit, they emit sort of a sinusoidal wave if they were at the same distance, and that's what you see initially. But if it's this runaway process, they're getting closer together. When they're getting closer together, that means that the frequency of the waves is increasing, but the amplitude is also increasing. And you see that here. So the waves are getting shorter in period, so the frequency is increasing, the amplitude is increasing. And this sort of amplitude frequency increase is called a chirp. And it's very characteristic of a runaway in spiral. And so this is now another depiction of this. So if you now, this is as a function of time. And again, notice the time. This is seconds. So this whole event happened just in a few milliseconds. But now this is on a spectrogram, so time versus frequency. So this ramping up of this wave in frequency with this characteristic shape is called a chirp signal. And incidentally, you can play it. This sort of occurs in the audio range. So often they say we hear the universe in gravitational waves as opposed to observe it. And I couldn't embed this in thing, so I'll go to YouTube for that. But so this is now converting the signal to sound. Do you hear the whoop, the blip? So that's what black hole mergers sound like. It's actually kind of wimpy, right? And so the first sound, the lower frequency, that was at the raw frequency, but it's a bit low for us to hear. So then they scaled it up to higher frequency so you could hear that chirp. But that chirp is very characteristic of an in-spiral. And in fact, the shape of this in-spiral tells you something about the masses of the black holes. And perhaps unsurprisingly, it's an unusual combination of the masses, but it's called the chirp mass. So by measuring this, the way in which the frequency ramps up, the amplitude ramps up, we get some information about the combined mass of the system. Now, the other bit of information from this that we can get immediately from this is, I think I went one past, is the peak amplitude. Right, so again, from this picture of this runaway in-spiral, so the frequency and amplitude are increasing, but it reaches a maximum and then it starts to decrease. The place where it was a maximum is in some sense when the two horizons touched. So this actually tells you, so one thing about black holes in relativity is that their size is linearly related to their mass. So a black hole that's twice as massive as the other one is just twice as large. And so if they touch, the size of the system is roughly like twice, the sum of the sizes of the two black holes, which is the sum of their masses. So this peak frequency, and so again, you can relate distances to frequencies through the speed of light. Essentially, the light crossing time tells you what the frequency is. So knowing what this peak frequency is actually tells you what the sum of the masses of the black hole is. And then using that together with the chirp mass, so the two different combinations of the two masses, you can actually figure out what the two masses of the black holes were. And it turns out that in this case, they were almost the same mass, but the total mass of the system was 65 times the mass of the sun. So these two black holes in total weighed 65 times the mass of the sun. But now the other aspect of the signal that you can see is that this ring down, this very rapid decay of the signal, and in fact the way it decays is also very characteristic of black holes. And it's actually a property of the merged black hole. So the fact that in about 2 cycles it vanished, so you can sort of measure how quickly it's decreasing, but also the frequency. It actually tells you what the mass and the spin of the final black hole is. And so from this measurement, what they found is that the final mass was 62 solar masses. So perhaps you're saying, oh dear, that's a problem. That's inconsistent with the 65 solar masses. But actually, it's completely consistent with the theory. And the reason is in this burst phase, about 3 solar masses worth of energy was emitted in gravitational waves. So initially, yes, there was 65 solar masses worth of energy, but 3 solar masses got streamed away as gravitational waves. And incidentally, this is not coming from inside the black holes. This is the energy in the space-time around the black hole. So it's completely consistent with nothing being able to escape the black holes, that energy is coming outside of the system. But if you think a little bit about that, that's incredible, right? So in a few milliseconds, three suns worth of energy, like E equals mc squared, was converted into pure energy. And actually, if you compute it in terms of luminosities and compare it to other things that are bright, like stars, it turns out that this one event in this fraction of a second outshone all the visible light in the universe combined. So all the billions of galaxies with all the billions of stars was not as bright combined as this one single puny little blip. That's the chirp. So in an astonishingly energetic event, and the reason why this isn't dominating all of the these events aren't dominating the energy of the universe is that they're actually very, very rare. They don't happen very often. So this kind of energy is not flooding throughout the universe very frequently. Now the other thing that you can get from this is the amplitude. So more information you can get from it is how far away it was. And this also gets to how remarkable the LIGO instrument is, and I won't really have time. I won't have time to go through it, but I'd recommend you invite someone who talks about the instrument. But so this amplitude here, the strain. So if you see the axis, it's in units of 10 to the minus 21, which is the fractional change in the arm lengths of LIGO. So 1 part in 10 to the 21. And it turns out that that's something like the 1,000th the diameter of a proton over the 4 kilometers length of LIGO. So an incredibly minuscule change. But the theory tells us that where the black holes collided, the fractional distortion in space-time was of order 1, of order unity. So it was a very large distortion, but the theory also tells us that it decays like 1 over the distance from the source. So going from 1 to this 10 to the minus 21, we can estimate how far away it was. And if you work through the numbers, it turned out that this event was about 1.2 billion light years away. So just in this little wiggle, we can get all of that information about this event. If you begin, and say, it's up to you to say, like, well, how good do you think that evidence is that these are black holes? But this is what the gravitational waves detectors are telling us. Okay, so in conclusion, so I hope if you didn't think they were bizarre and remarkable before, I hope you think that black holes are bizarre and remarkable. The one thing that I found fascinating, even before the discovery by LIGO, is if you look at the history of general relativity, so Einstein never believed in these black hole solutions. He thought that they were mathematical curiosities. They were just too strange to be correct. And there was a lot of misunderstanding about even the nature of these solutions, I'd say before the 60s. So it was really, black holes were not even considered to be physically real before them. But after the 70s, once these astronomical objects came around, our center of our galaxy, these stellar X-ray binaries, I think things almost went too far the other way, that black holes became, at least in the scientific community and sort of the astrophysics community, well, they were obvious, they had to be there. And also the theoretical physics community with, you might have heard about string theory and the black hole entropy and the information. And so there's some remarkable connections between black hole physics and other sides of physics where people thought, well, they have to exist. They're just such natural, beautiful objects. But I think things went way too far, from a scientific perspective, that the evidence wasn't supporting that. And I think now finally, 100 years after Einstein, we're starting to get a new direct probe of strong field gravity in the vicinity of black holes. And the evidence right now, so I explained sort of in words and things like how we'd interpret that. You can do more quantitative estimates. And if you say, well, if we wanted to put a number, these aren't very precise confirmations yet. But this is just the beginning of a whole new era of observing the universe through strong field gravity. So I think the best is yet to come. Thank you.